Good afternoon, everybody. This is going to be the second video, or we're going to be attacking our second Let's Calc video. This time we're going to be looking at some selected problems and exercises and questions from the second assignment, which focuses on using algebraic limit techniques, which we oftentimes colloquially call trimming the quills in my class. So basically, let's jump right in with our first question. Let's click awkwardly and have nothing happen. Okay, so the first question we're going to attack is not one that I would say is particularly difficult. It's more that I want to illustrate what the technique is that we're doing here, just so you've seen it a couple times. And I made sure on the written solutions to go through everything in painstaking detail and show it all as carefully as possible, but I figured it would be good to talk about it once before we look at a harder question from this section. So in problem number 5, I think it's actually 4, 5, and 6, it appears that you're given information about the general behavior of two different functions, f and g, around x equals 6. One goes towards 3/2 and one goes towards -10. Then it asks you to use that information to evaluate the limits of some other new functions that we've created out of f and g. Combinations, I think, is what I was looking for. Who knows? It still feels early. So in here, the first question that you're tasked with, or the first expression you're tasked to go with, is you want to evaluate the limit as x goes to 6 of g of x squared plus 4f of x. And again, although I feel like most people could get to the evaluation step really quickly here, say for a little bit of arithmetic, I think it's important to remind you what is actually happening underneath these limit property application problems, at least with one simple one. So in a sense, what you have to do is every single time you attack, or as you're working your way through this limit property question, your job is to think about what limit property you're using each time. Even if you don't show every step in painstaking detail, you should still think about what step you're actually doing. So for instance, when I look at this, I see the limit as x goes to 6 of some function plus another function. So first I'm going to apply the limit sum and difference property. So I'm going to write this as the limit as x goes to 6 of g of x squared plus the limit as x goes to 6 of 4f of x. In a sense, what we've done is we've taken advantage we've taken advantage of the fact that the limit of f plus g is equal to the limit of f plus the limit of g. That is the sum and difference property. So at least it's just kind of nice to remind you what it is that's happening there. The second thing I'm going to do is I'm going to take advantage of two other properties. The first property I'm going to take advantage of is the exponentiation property. So 2 is just a real numbered power, which means we can rewrite this first one as the limit as x goes to 6 of g of x all squared. So in other words, we can go from the limit of a function squared to the square of a limit of a function. On the second one, we're also going to do another limit property. Specifically, we're going to take advantage of the scalar multiple property, which says we can bring a scalar multiple out in front. In this case, it's the 4. And we can multiply 4 times the limit as x goes to 6 of f of x rather than the limit, and get the same value as the limit as x goes to 6 of 4 times f of x. Neither of these properties should be completely brand new, but it's important to recognize that we use both of them. So we use basically the power property, and then we also used the scalar property, or the scalar multiple property. So with both of those in place, we're now in position to make some direct substitutions. So notice at the very top, we said the limit as x goes to 6 of f of x is 3/2, which means this will be 4 times 3/2, because that is the limit as x goes to 6 of f of x. On the other hand, we did say as well, or we were told or informed, that the limit as x goes to 6 of g of x is -10. So this would just be -10 squared. So in looking in here, all that's left is the arithmetic, although again, as we've mentioned a couple times already this year, that's an acceptable answer, that is correct. But to simplify a little bit further, we're going to get 100 plus, 12 over 2, which is going to be 100 plus 6, which is equal to 106. And so there is the value of that combination of the functions f and g squared plus 4f of x. And it turns out our limit of this new function is 106. And all we had to do was use the limit properties. And again, I can imagine many of you would just literally enter the problem right here and just kind of jump in there. And I get it. I understand why. But keep in mind that the stuff that happens above there, all the stuff right here, that's what's actually happening when we apply the limit properties. It's important to at least understand that that's there, and maybe even think it through as you do the problems. So there it is. There's question number 5. Okay, that brings us to number 7. And 7 is a much harder question. And this is one that typically 90% of the questions students ask on the day after the assignment's given out. They all come from question number 7. And now we've talked about it a little bit more in that first assignment. There were videos focused on this idea. But I want to talk about one more time, once again, just kind of remind you what's happening. So in this situation, we're looking at the limit as x goes to -1, which is an interesting and strange thing to be given, considering we were told information about the limit as x goes to 6. But bear with me. And it says the limit as x goes to -1 of 3f of x plus 7 plus x, all divided by -4 g of x plus 7. So once again, we have a combination of the functions f and g, but this time we also have some shifting going on. We can see that we've got that x plus 7 and x plus 7 that we have to deal with here. So we're going to have to make do with what we have. So what I'm going to do though first is I'm once again going to remind us about the limit properties. First property I'm going to use is the quotient property. It's going to be the limit as x goes to -1 of 3f of x plus 7 plus x all over the limit as x goes to -1 of -4 g of x plus 7. So I'm starting here because, of course, that is our first property, but I'm not going to stay there. In fact, I'm going to do a couple properties in one step in this case, be a little bit more reasonable here in my expectations. The first thing I'm going to do is move this limit over a little bit, because I'm going to pull out that scalar of 3. Basically, what I'm going to do is I'm going to apply the sum and difference property as well as the scalar property right off the bat. So this will be 3 times the limit as x goes to -1 of f of x plus 7 plus the limit as x goes to -1 of x. And I think it's really important to do this step before we think about the transformations, because having that x in there actually could pose some issues if we weren't careful, since it's not being transformed in the same way as the arguments of f and g are. Now down below, we can do the similar work. We can pull out the -4 using the scalar property. We'll do the limit as x goes to -1 of g of x plus 7. Now in this situation, I would hope that you could kind of infer what to do. It must be that the limit as x goes to -1 of f of x plus 7 is in fact going to the same thing as the limit as x goes to 6 of f of x. We should be able to make a substitution from there. But it's important to think about why it is that that's actually happening. And I think a good way to go is to look at it this way. As x goes to -1, x plus 7 must be going towards -1 plus 7, which is equal to 6. In other words, even though we're talking about x going towards -7, in a sense we can think about this as kind of its own little behavior happening. So we could, in a sense, reason out that this is the exact same thing as what we started with. This is just the limit as x goes to 6 of f of x, and this is just the limit as x goes to 6 of g of x. But for the sake of argument, and because this kind of comes up later on, not necessarily in the first half of the course, but later on, I think it might be useful to think about this as using a secondary variable. So instead, I'm going to make a substitution. And the variable that's used most commonly in substitutions in calculus is typically u, at least for an initial substitution. So what I'm going to do is I'm going to let u, I'm sure there's a joke in there, I'm going to let u equal x plus 7. So there's my thought process here. The reason I bring that up then is, as we said, as x goes to -1, u, which is equal to x plus 7, has to go towards 6. And I'm going to keep that in there and use that because that means that we can rewrite our limit a little bit. Up in the numerator, we can write this as 3 times the limit as u goes to 6 of f of u. And then, of course, it's still being added to the limit as x goes to -1 of x. Like, we haven't made any substitution there, but that's okay. It's a separate limit. Down below, we can follow the same pattern. We can write this as -4 times the limit as u goes to 6 of g of u. And now someone might make the argument and question the fact that we're doing limits in terms of u, but keep in mind it doesn't really matter what the variable is. As long as we have the limit of a variable going towards 6 of f of that same variable, we could change that t into whatever variable we wanted. If we wanted to call it q, we could think of this as the limit as q goes to 6 of f of q, and that would be equal to 3/2. And we could likewise do the same thing over here. We could say the limit as t goes to 6 of g of t is equal to -10. In a sense that x, while being an independent variable, could go by any name. It doesn't matter what name it goes by, we're still having the same behavior because f is still defined or has the same established pieces. So with that in mind, we are now ready to make our substitutions. It's going to be 3 times the limit as anything goes to 6 of f of that anything, which in our case is 3/2. This will be plus the limit as x goes to -1 of x, which is just -1. And in our denominator, we'll have -4 times the limit as stuff goes to 6 of g of stuff, and that would just be -10. Simplifying and cleaning this up a little bit, we get 9/2 minus 1 over 40. If we write that minus 1 as minus 2 over 2, we're going to get 7 over 2 over 40, which is equal to 7 over 80. And again, I've made that really complicated. There are lots of ways you could think about it just using transformations and just thinking about what x does and what x plus 7 does, how those move the functions around. But I think it might be a nice opportunity for you to see some substitution work done as just as well. So whatever way you attack it is fine, as long as you get the correct answer. Okay, that next brings us to question number 8. 8 used to be a multi-part section, but when I redid the assignments just last night, I rewrote it and just kind of focused on one because I think the concept of what's here is what's most important, but it's not the same kind. It's not going to be assessed the same way as everything else. It's more conceptual idea than anything else. So in question number 8, the question asks you or tells you first to find a piecewise function p of x that agrees with f of x at equals some rational function at every point except at x equals 1. Then they want us to evaluate the limit as x goes to 1 of f of x. So, in a sense, this is just the underpinning of how we work when we perform those algebraic limit techniques, when we quote-unquote trim the quills. So in here, what I want to think about and what I want to focus on first is what f of x looks like if we break it down into pieces, if we decompose it in a sense. So if we look at that, x squared minus 10x plus 9 is x minus 9, x minus 1. And then the denominator, we get x plus 1, x minus 1. Now, in looking at this decomposed version of f of x, we can see that there is in fact some sort of issue at x equals 1, which might motivate us to try to find another version of the function out there. Specifically, if we tried to find f of 1, we'd get it something that's indeterminate, specifically something that's undefined. F of 1 goes towards 0 over 0, which is not a number, so we can't even say it's equal to that. It just doesn't give us a value. So what that's telling us, and what we're seeing evidence of, is that there's going to be a hole at x equals 1. And if there's a hole at x equals 1, that means that we can't necessarily find the limit by direct substitution. In fact, we definitely can't find the limit by direct substitution. Instead, what we want to think about is what function behaves exactly the same as f of x, just not at x equals 1. Because the idea would be if we could write it as a function that behaves the same way every single place except for 1, we could find the general behavior and the limit and just attack it using that technique. So in a sense, here's what we're going to do. We're going to point out that f of x, if you divide out those x minus 1s, is the same thing as x minus 9 over x plus 1. So let's decide, in fact, let's even do it this way. We could even think of f of x this way. It's not going to give us the p of x right away, but bear with me for a second. F of x is undefined when x equals 1. We just talked about why, because that hole that's there and that factor of 0 that arises. But in a sense, if x isn't equal to 1, we end up with this. We end up with x minus 9, x plus 1. So the idea is, because this portion of the piecewise function describes the general behavior, we can actually attack this thing and evaluate the limit just by using the general behavior. So to get there, of course, we could actually use the general behavior. In a sense, we can answer the second part of this question first. The limit as x goes to 1 of f of x by trimming the quills or using the factoring technique, however you want to think about it. That's the limit as x goes to 1 of x minus 9 over x plus 1, which is 1 minus 9 over 1 plus 1, or negative 8 over 2, or negative 4. So in a sense, we've answered the second part of the question first. We just evaluated the limit as x goes to 1 of f of x, but we haven't written that other function. But in a sense, we already have. We just haven't thought about it as a separate function yet. That function that agrees everywhere except at x equals 1, p of x, is going to be the function x minus 9 over x plus 1. Because we've already established that these two functions look exactly the same. There's just that one single dot that's there. It's almost like in those old sci-fi TV shows when an evil twin would show up and it was exactly the same, a total replica of the other person except for the evilness, outside of like a goatee. It's kind of like that one spot was the goatee. That's the only difference between these two functions, but one of them allows us to easily find the limit. And in a sense, this is just what trimming the quills is doing, is identifying this function. And there we go. We now have found p of x, and we've also found the limit. We technically didn't need p of x for it, but it's just kind of nice to see that it's there. And so again, this is the foundation of that trimming the quills technique that we've been using and working through in class. Okay, next, Brings us to our next couple values, specifically our next couple questions. These come out of the actual evaluation of limits using these algebraic techniques, and I really wanted to illustrate a couple of them. I didn't want to do every single one because I think some are pretty simple, but I really wanted to illustrate them because there's important formality and there's a formalism you have to adhere to when you're evaluating limits this way. You've got to be really careful with what we call linkage errors and not abusing the equal signs power. You've got to be really careful that you do everything carefully. So I've chosen a few of these examples. I haven't chosen every single one or the hardest ones. I've just kind of chosen a representative sample of questions as well as some ones that evaluate and offer a few little tricks to it. So let's start with number 11. So it tells us to evaluate each limit. It says don't just trim the quills, check for an indeterminate form first. It's a good place to begin. So when I go to check for an indeterminate form, the first thing I want to do is I want to actually check whether or not we get 0 over 0. Because if we don't, then we don't need to continue. We can just stop and evaluate it by direct substitution. So in here, if we use direct substitution with x equals 5, we're going to get 3 over 2 minus 15 over 10, which is, of course, 3 over 2 minus 3 over 2. That equals 0. Now, that doesn't automatically mean that we're done, that we have an indeterminate form. We've got to make sure the denominator goes to 0 as well. So we ask ourselves, does 5 squared minus 25 equal 0? Yeah, it does. So that means we have an indeterminate form, which means this is a candidate for us to use one of our limit evaluation techniques, or quote-unquote to trim the quills. So in looking up here, I see rational expressions. In fact, this is what we'd call complex fractions because there are fractions in the fraction. So in fact, what I'm going to use is I'm going to use the common denominator technique. I'm going to try to rewrite the numerator as a single fraction and see if that won't allow for some simple cancellation for us to go through. And the hint is this technique should work. If you get 0 over 0 with a rational expression, it should always break down in exactly this way. So in looking here, what I'm going to do is I'm going to have to start writing some of my pieces in here. I'm going to try to do this in a reasonable manner, but without skipping any too significant steps. What I'm going to point out here is, first and foremost, I want a common denominator in my numerator. So if I multiply up and down by x on that left fraction up there, 3 over 2, I'm going to get a numerator of 3x minus 15 over 2x. And then all of that is over x squared minus 25. Now I realize I can factor that denominator. I'm just kind of holding off for a second because I want to try to crunch it together a little bit better first. So there's my first step. The next thing I want to point out is that we can transform this into a single rational expression now that we have a fraction divided by another piece. So think for a second here about what that would look like. If we are doing 2/5, let's say, divided by 10, that's the same thing as 2/5 divided by 10. And remember, when you divide by fractions, it's the same thing as taking the first fraction and multiplying by the reciprocal. In other words, we would get 2 over 5 times 10, meaning that these two denominators end up forming the same denominator. They both stay in the denominator in this case. And the reason I want to bring that up is I can transform this into that single fraction. Write it as 3x minus 15 over 2x quantity x squared minus 25. So everything looks good so far. Now all that's left is for us to do the lighter factoring, the stuff that Math 7 and Math 8, possibly even Math 1 and 2, whatever course it was that you learned to factor, they prepared you for. This is going to be the limit as x goes to 5 of 3 quantity x minus 5. That's a good factor to see in the numerator because we're looking for what's causing that 0 over 0. In our denominator we have 2x, and then x squared minus 25 becomes x minus 5, x plus 5. And once again, this is a victory. X minus 5 in the numerator, x minus 5 in the denominator. They can make a 1, they divide to 1, which leaves us just the cleaner limit as x goes to 5 of 3 divided by 2x quantity x plus 5. With that in place, we can now plug in directly. Because our numerator is never going to be 0, we can't possibly get 0 over 0 anymore. So instead, by direct substitution, in this function that, by the way, agrees everywhere except x equals 5, might as well point that out, we're going to have 3 over 2 times 5 plus 5. And of course, as we mentioned, this is a correct answer. You could submit that as your final answer, but we're so close. Let's clean this up just a little bit. This is going to be 3 over 10 times 10, which gives us our final answer of 3 over 100. So that's telling us that the y value of that rational complex fraction is approaching 3 over 100 as you approach x equals 5 from whatever side you want to. So there it is. A couple things to point out here, little places that are there. A couple things to note. First, when I checked the indeterminate form, I did not write something like equals 0 over 0. You can't do that because 0 over 0 is indeterminate. It's not a number. You can't say something with a numeric value is equal to something that is not a number. So be careful. That's definitely not true. And second, notice, because I used equal signs, for every equal sign, I had to maintain that limit every single time, at least until I replaced the x's with the 5s. As soon as I replace the x's with 5, all the x's, by the way, not just a few of the x's, I have to maintain that limit notation in order to be doing this correctly. So just something to keep in mind as you're working your way through. This is important. On an exam, you could lose points. You would lose points if I caught you making any of those things called linkage errors. You can't link two things that are not correct. No better than you can say 10 equals 42. Nice as that would be. So there's question number 11 worked out in full. Okay, that brings us to question number 12. 12 is a perfect counterpart to the last one. It's just the rationalization technique. I can tell because of the radical down there in the denominator. So my goal here is, of course, to first check if it's indeterminate, because if it's not, I can save myself a whole heck of a lot of trouble. Once I determine it is, though, then I can go through and trim the quills and perform some algebraic manipulations to find a function that agrees everywhere, except in this case, at x equals -8. So to attack, before I do, I make sure it's eligible. I need to make sure I need to do this. So if we do x plus 8 in there and we evaluate as x goes to -8, we get -8 plus 8, which is 0. In the denominator, we get the square root of -8 plus 17 minus 3. That's the same thing as root 9 minus 3, which is definitely equal to 0 as well. So this is eligible for us to trim the quills. It's necessary for us to go through, 0 over 0 being indeterminate and all. Let's go and start attacking. So at this one, I'd say that the biggest issue that I see every year as students work through this is sloppiness and laziness with parentheses. You have to use parentheses when you're attacking this problem. When you start off and you're just looking at it for the first time, you can probably get away with it. It's not the end of the world. This is all fine. But the problem is, this radical in the denominator is hiding from us that factor we're looking for. And since we've got an x going towards -8, you can imagine the factor we're looking for is an x plus 8 somehow from the bottom. We hope that it's in there. In order to get there, we're going to multiply up and down by the conjugate. When we do, we need parentheses around each of those factors. Otherwise, we might distribute something incorrectly. So first, our conjugate is going to be the same thing as the original denominator. It's going to involve the square root of x plus 17 and 3, but instead of being minus, it's going to be plus. That way we can create a difference of squares and take advantage of the structure of difference of squares to eliminate that square root. Now, if we multiply the denominator by it, though, we also need to multiply the numerator by it. And so this gets us, this is one of those, like, be patient, it gets better. Like, this is bad right now. But of course, our structure here, the value of doing it in this way, is that while our numerator has become our least favorite friend, the denominator, being a difference of squares, transforms into the square root of x plus 17 squared minus 3 squared. And again, still doesn't look much better, and I know I'm being painstakingly careful here as I work my way through, but while our numerator remains annoyingly crunchy, our denominator becomes x plus 17 minus 9. And you will, of course, note that that is the same thing as x plus 8. With that in place, the x plus 8s divide away, so we're able to divide those off, and that means our limit is equivalent to the limit, as x approaches -8, of simply square root of x plus 17 plus 3. And that has no denominator, so we can't possibly get an indeterminate form. In fact, we can just plug in directly. And again, notice I'm just now able to stop the limit notation because I just plugged in -8. Up until that point, anywhere where there was an x, I needed that limit notation. This gets us the square root of 9 plus 3, which is 3 plus 3, which is 6. So that's saying that the y values are approaching y equals 6, or the function is approaching y equals 6 as x approaches -8. And again, if you're thinking about this in terms of functions that agree, this function, square root of x plus 17 plus 3, agrees with our original function everywhere except for that one x value, -8. So there you go. There's question number 12. So you've gotten to see a rationalization one. You've gotten to see a, common denominator technique one. Okay, that brings us to 14. 14 is not actually difficult. In fact, I think it's probably easier to compute than either of the two previous problems. The algebra is pretty simple, but there are common mistakes that happen all the time, and this is one that kind of lays the foundation for why we're doing limits. This will help us through when we get to the next chapter, which focuses on slope. In fact, if you recognize this, you might have even seen this difference quotient kind of thing before. In any event, though, we want to evaluate the limit as h goes to 0 of quantity x plus h squared minus x squared, all divided by h. Now, as usual, it doesn't matter what variable we're dealing with. Before we start, let's plug in and direct substitute and make sure that this needs us to address with an algebraic technique. So if we plug in h, or if we let h go to 0, this becomes x plus 0 squared minus x squared, which is the same thing as x squared minus x squared, which is 0. And then in the denominator, if h goes to 0, h is 0. So this definitely does require us to work through this algebraically to quote-unquote trim the quills. So let's do that. So in attacking this, before we can do anything else, we could use a difference of squares. In fact, I've never actually seen that before, but you could write this as a difference of squares and get this to clean itself up. That's actually really interesting, but I'm gonna be patient. Instead, I want to focus on what x plus h squared is equal to. So, because this is typically that place where people make mistakes. Remember, x plus h squared is x plus h times x plus h. And that means if you're into the old FOIL method, you could do it that way. You could also look at it as a polynomial or an old school multiplication. In other words, you'd get x squared plus xh plus xh plus h squared, and you'd end up with x squared plus 2xh plus h squared. So it's important to have that correct because our numerator has to be expanded for us to be able to see the cancellation or the zeroing out that we're going to need to clean this up. So our first part becomes x squared plus 2xh plus h squared. It's all minus x squared, and that denominator just stays h. Now from here, we're going to have to evaluate this limit one more time, I think. But notice, x squared minus x squared zeroes out automatically. So we're really going to evaluate the limit as h goes to 0 of 2xh plus h squared all over h. And although you might be able to do this by dividing both terms, what I'd love to point out is that this actually factors. There's a GCF in the numerator of what? H. So I'm going to pull out an h. That'll leave me 2x plus h. And in my denominator, I'll still have h. And those h's divide to 1, which means that we're really evaluating the limit as h goes to 0 of 2x plus h. And at this point, we can plug in h equals 0. We'll get 2x plus 0, which equals 2x. So this obviously feels a little bit weird when you're going through it. It's the first time your limit isn't a numeric value. What we've actually just found is the slope of a particular function, but that's neither here nor there. It will be there like in a week and a half. So for now, you've seen it in action. There is that technique with a difference quotient style problem. It's a little bit different than before. Okay, finally, I think the last one out of this selection, out of this portion where you're evaluating limits, comes up in question number 15. It asks you to evaluate the limit as x goes to 0 of 2x minus root x over x. And now in my solutions, my written solutions, I did this in a particularly clever way. I'm not going to go with the cleverness here. I'm just going to offer it in the more traditional path. So first, if I plug in 0, I get 2 times 0 minus root 0, which is clearly 0 minus 0, also known as 0. In my denominator, I get 0. So in here, as I look, what jumps out to me first is the fact that I've got a square root, and square roots make me think of the rationalization technique. So unless you've had kind of the same epiphany I had when I did the written solutions, let's go with rationalization and see where this leads us. So of course, in our denominator, we have x, and our numerator, we have 2x minus root x. But I want to get rid of this and change this and factor it all out and clean it up, so I'm going to multiply up and down by the conjugate. The conjugate will involve 2x and root x, but this time it'll be a plus instead of a minus. And of course, if I do it in the numerator, I have to do it in the denominator as well. So cleaning all this up and multiplying it out to start to play with a little bit, we're going to get 4x squared. I'm doing the difference of squares here, by the way. That's 2x squared minus root x squared. So we'll get 4x squared minus x over x quantity 2x plus root x. Now up there, I see a GCF of x, which is a good thing. It's always nice to have a GCF of x. It's nice to pull out. We'll have x quantity 4x minus 1 all over x 2x plus root x. And notice those x's divide away, which means we're actually just evaluating the limit as x goes to 0 of 4x minus 1 over 2x plus root x. Now here's the thing though. If we go to perform direct substitution, we get 0 minus 1 is negative 1 in our numerator. And in our denominator, we get 0 plus 0, meaning that this limit is equal to negative 1 over 0. Unfortunately, that's not indeterminate where we just have to do a little bit more. We just have to work a little bit harder. That is actually undefined. Basically, what this is telling us is that the limit is going towards, it looks like, negative infinity at this point. You could also say that this limit does not exist. So unfortunately, this limit isn't going anywhere. We're not going to get a nice pretty answer like 3/7 at the very end. We're just stuck going through and turning out that, hey, there was just something that was fundamentally wrong with this that even trimming the quills couldn't resolve. So interesting, challenging kind of question, but it's there for you. Okay, the next question that we get to is question number 18. Question number 18 is a challenging question. I've never asked this on a homework assignment before, but I think it's the kind of thinking that would be valuable to go through. It helps you really reason out what you understand about these algebraic techniques. Question 18 states, let g of x be equal to kx minus 32 over x squared plus 3x minus 28, where k is a real number. It then tells us that the limit as x goes to 4 of g of x is 8 over 11, and it wants us to find the value of k. So in here, as we go to look through, it would be valuable for us to start by looking at what happens if we just try to evaluate the limit as x goes to 4 of g of x. So if we start to attack the limit as x goes to 4 of g, which we see is equal to kx minus 32 over x squared plus 3x minus 28. The numerator goes to k times 4 minus 32, which is 4k minus 32. But our denominator goes to 4 squared plus 3 times 4 minus 28, which is 16 plus 12, or 28 minus 28, which is 0. So now what this is telling us is that our limit appears to be going towards, we seem to be getting 4k minus 32 divided by 0. And then somehow that's supposed to be equal to 8 over 11. Yeah, that's not good. That's not ideal. What that tells me is that we have an issue with the value of k. There's only one specific value of k that's going to work that's going to allow us to evaluate this and get 8 over 11. And how, you might ask, can we get that 0 in the denominator to an 11? By, of course, trimming the quills. If we have just the right value of k in the numerator, we can actually have this limit equal 0 over 0. So what we have to do in order to solve this is we have to figure out what that value of k is that makes the numerator go to 0 simultaneously with the denominator. Because if the numerator and denominator both go to 0, we have an indeterminate form, and we can use algebraic techniques to clean this mess up. Well, let's focus on that equation. I don't know why I undid it. If 4k minus 32 equals 0, that means that k is obviously equal to 8. So my thought is k must be equal to 8, because that's the only value for k that will make the numerator and denominator simultaneously 0 over 0. So I'm going to box it and call it an answer, but let's just say that I don't trust it. I'm not a very trusting person. Weird things happen sometimes. So let's just see what happens if we try to evaluate the limit as x goes to 4 of 8x minus 32 over x squared plus 3x minus 28. If we go to evaluate this, we can factor it. We already saw that it's going to be indeterminate by determining what value of k was necessary. Our numerator becomes 8 quantity x minus 4. Our denominator becomes, let's see, if we want to multiply to negative 28 and add up to 3, I'm thinking x plus 7, x minus 4. Oh look, the x minus 4's divide away. We're really looking at the limit as x goes to 4 of 8 over x plus 7. And if we evaluate that, we get 8 over 4 plus 7, also known as 8 over 11. So in fact, this did in fact check. We've done everything correctly so far, and we found the correct value of 8, or of k, which turned out to be 8, in order to make this limit evaluate as they told us. So a little bit of a trickier thinking, but actually pretty easy to do algebraically. You just had to recognize that if you want something over 0 to go to 8 over 11, you've got to make sure the numerator goes to 0 as well to have any chance. Indeterminate means we just don't know yet. So that was our key. Okay, finally, this brings us to the final question that we're going to look at here, and also the final question of the assignment. This is question number 19. and it gives you a graph in this case, so there's some graphical work here as well. It says let g of x be the piecewise linear function graphed at right. So I see a couple line segments. I see 3 line segments. I also see a couple open dots, some closed dots, a bunch of different stuff here. So if memory serves, the first couple questions are simple. It gets a little bit harder after that. So let's dive right in and see what happens. So the first question, 19a, asks us to evaluate the limit as x goes to 3 of g of x. So 3 is right here. So I'm thinking about the behavior of the function around 3. As we approach 3 from the right, we seem to be going to y equals 1. As we approach from the left, we seem to be going towards y equals 1. This limit is going to be equal to y equals 1. Simply review from yesterday or the first day's assignment. For question 19b, we want the limit as x goes to 1 of g of x. So we approach x equals 1. As we go from smaller numbers, we approach y equals 3. As we approach from bigger numbers, we approach y equals 1. Unfortunately, that means this limit does not exist because we're approaching 2 different values as we get closer there. So there's no consensus of what's happening. So again, just review from yesterday. Here's the good stuff. So first for 19c, it doesn't even mention limits. It just says find all x values between -5 and 5 such that g of x is equal to 0. So we're basically looking for the zeros of this piecewise linear function. So as I look up here, I see 2 places. One appears to be right there, and the other appears to be right there. So we have one negative x value, one positive x value. For the negative x value, it sure as heck looks like -2. As I look, though, we can confirm that that's true by looking at the slope of this line. This line goes up 1, 2, 3, 4, and over 1, 2, 3, 4. So moving up 1 over 1 to stay with the same slope of 1 over 1, we definitely get to -2. So we definitely have x equals -2 given almost directly on our graph. So there's one such value. I won't box it yet because technically there's one more. For the other side, I'll just write that in there. The other side, we have a different kind of graph for us to look at. So over here, when we're on the interval from 3 to 5, actually looks like for x greater than 3. So let me make a quick change there. For x greater than 3, we have a linear function once again. And we can go through and figure out what we know about that linear function by looking at the slope of the line, as well as constructing an equation for the line. So the line that's over there is going to be given by the equation y minus y1 equals the slope times x minus x1. It's called point-slope form. We've mentioned it before, but still. So I want to know when that whole thing has y equals 0. But to get there, I just want to fill in all the points first. So first and foremost, I'm going to use the ordered pair right down there, which appears to be 5, -2. So that's going to serve as my x1 and my y1. So y minus a -2 equals our slope, x minus x1, which is 5. Now our only question is the slope itself. And to find my slope, I'm going to go down 1, 2, 3, just 3. So 1, 2, 3, and over 1, 2. So it looks like our slope is going to be -3 over 2. So if we wanted to write this equation of the line, we'd have y equals -3 over 2, quantity x minus 5, minus 2. And now remember, we were looking for the zeros, so we need to figure out at what x value this is equal to 0. So solving this equation around, we're going to get -3 halves x minus 5 is equal to 2. I can multiply both sides by 2 over -3. So that's going to give us x minus 5 is equal to -4/3. And then if we add 5 to both sides, we're going to get that x is equal to, let's see, 15, or let's go -4/3 plus 15/3 is equal to 11/3. So basically we had our first one, x equals -2, given quickly. Our second one we had to do a little bit of work with by finding the equation of the line that was right there. In any event, we can now say that g of x equals 0 at x equals -2 and 11/3. So definitely a little bit challenging, but interesting for sure. And this ability to quickly construct a line or a linear equation or a part of a piecewise function's linear equation in order to find a value is an essential skill that you'll definitely need going forward. And last but not least, that brings us to the final question, 19d. This one starts by defining for us the function p of x. It says let p of x equal x to the fourth minus 16 over g of x, and it wants the limit as x goes to negative 2 of p of x. So in order for us to attack this, it's important for us to look at what's happening on g of x around the limit as x goes to negative 2. So a couple little things here. First and foremost, when you have x less than 1, g of x is going to be a line. And that line we can establish. We already talked about the fact that its slope was 1. So this has a slope of 1 because we go up 1, 2, 3, 4 over 1, 2, 3, 4. So our slope is 4 over 4, or 1. And it goes through the y-intercept of 2. So our line is actually going to be x plus 2. So once we have that as our line, we can rewrite p of x and point out that p of x equals x to the fourth minus 16 over x plus 2 when we have x less than 1. From there, if we want to evaluate the limit as x goes to negative 2 of p of x, and I won't even write p of x, I'm going to save myself one line, of this, we can first, of course, check by direct substitution. We're going to get negative 2 to the fourth minus 16, which is 16 minus 16, or 0. And down below, of course, we get negative 2 plus 2, which is 0. So this requires some of the trimming the quills algebraic techniques. We got a factor. Now our denominator's clean. Our numerator is a difference of squares. So first that'll be x squared minus 4, x squared plus 4. But x squared minus 4 can factor itself a little bit more. So we'll do the limit as x goes to negative 2 of x plus 2, x minus 2, x squared plus 4, all over x plus 2. And as we've seen so many times today in this assignment, the x plus 2's divide away. Means that we're actually evaluating the limit as x goes to negative 2 of x minus 2 times x squared plus 4. And if we go to evaluate this thing, we're going to have negative 2 minus 2 times 4 plus 4. And of course, this is a correct answer already, but for clarity, we get negative 4 times 8, which is negative 32. So we're able to find our limit value. We just had to once again find the equation of a particular line segment and work our way through from there. So with that said, that completes our work through the work that I'm doing with you, the video solutions for the second problem set, the Algebraic Limits problem set. Hopefully these have been illuminating and helped you conquer this assignment as well as anything else. Have a good day.